Hello, everyone, and good morning from Vancouver, British Columbia. So my name is Jess McIver. I'll be your session chair today. I'm very excited about the lineup of speakers that we have for you. So a quick announcement. So in case this is your first parallel session in Amaldi, so we do have the chat enabled here in the parallel session. So we're asked to please use the chat for asking questions. So if you would not like to voice your question by speaking it, then please either indicate that for me or please ask it anonymously. And you're also free to chat with the speakers and other participants to follow up after a talk. So we are going to go ahead and get started with our very first talk this morning, at least here in Pacific time. So Catalina Miritescu will be telling us about magnetic noise injections and preliminary results for the Virgo detector. So please go ahead and share your screen, Catalina, and take it away.
Okay, thank you, Jess. All right. So hi all, my name is Catalina and I will be talking about the work we've been doing with the environmental noise hunting team at Virgo and about some magnetic noise injection scripts that we developed and preliminary results that we managed to obtain for the detector. A brief outline of the talk, I will very briefly cover the motivation for developing these scripts and for the injections that we did. The equipment that we used for the injections, then I will go into detail into each of the scripts and what parameters are necessary to run each script, what exactly the injections represent, and then we will look over the preliminary results and the next steps and future work that needs to be done. Well, as I assume you all know, a little bit about Virgo. It is an L-shaped interferometer. We use it to measure incoming gravitational wave signals, and this measurement is based on a very, very tiny changing length that is produced in the two different arms of the interferometer. In this detector, we have a lot of electronics, a lot of magnets, a lot of computers. They all produce magnetic fields. And these magnetic fields could actually influence the detection, the measurement of the detector. We want to be able to characterize the environmental magnetic fields really well, and more importantly, to characterize the response of the detector when these environmental magnetic fields are present. There are a few critical coupling locations represented by the test masses, which have actual magnets attached. So you can imagine that an external magnetic field would heavily influence the position, the location of these test masses. The optical benches, wherever we have cables and we have inductance currents and magnetic fields, everything is going to be affected and coupled to the environmental magnetic field. Before the start of 04 for Virgo, we need to do some, and a few of them have already been performed, these magnetic injections campaigns, because as I said, we want to understand and characterize this response of the detector to environmental magnetic fields. While the 04 campaign is running, we also want to monitor how this response is gonna vary across weeks, and to do that we need to perform weekly injections and to calculate what we call this coupling function or transfer function between the magnetic field that is being measured by magnetometers inside the buildings, the central building and the two end buildings, and the response, what we see in the strain of the detector. The equipment that we used for the injections were these large coils. Each end building and the central building has one of these really large coils, and we used two different types of magnetometers. One is the triaxial Partington magnetometer. Tubes, they are single axial, so we have one black tube for each axis, for a vertical axis, north-south and east-west. In the N buildings, we only have available the big coil and the set of the single axial Metternich magnetometers, while in the central building, we have available the single axial magnetometers, a triangle in this image. We have available the big coil, which is on a terrace, a level above the whole magnetometer, the whole detector and the injection towers and all equipment. And we also added the Bartington triaxial magnetometers at particular locations of interest. Near the detection tower, the north input, west input tower, the beam splitter, and the injection bench. Here is where we expect the coupling function to have the highest values because of all the electronics and the magnets present around the detector at that point. To briefly describe the circuit, what we do, we have these injection Python scripts that are going to be sending the signals to a digital to analog converter. From the digital to analog converter, the DAC, the signal is going to go to an amplifier, which is going to amplify the power transmitted to the coil. The amplifier has some limits in both voltage and current intensity, so we need to be sure that we do not saturate the amplifier when we send the signals. These limits are 72 volts peak to peak and 6 ampere peak to peak transfer into some limits, some limiting values that we can input in the digital to analog converter. For low frequency, that value is 6 volts. For high frequency above 10 hertz, that value is 9 volts, with specification that in the northern building and western building, we don't only have to worry about the amplifier being saturated, but also about the magnetometers being saturated. The position of the magnetometers with respect to the coil is a bit different because these end buildings are smaller than the central building. So the magnetometers are closer, so they can more easily get saturated. That's why we have a limiting voltage that's 1 volts around 10 hertz, and then we can slowly increase it till 100 hertz when we can go to the full maximum voltage of 9 volts. And just an example of what I meant by saturated, in the upper right corner, we have a plot where we actually send a voltage that's higher than the limited voltage, and we obtain this plateau, which should not happen. First script and the first type of injections that I'm going to talk about are the so-called magnetic lines injections. What we do is that we send a sinusoidal signal to the digital to analog converter, and we have a few parameters that we can vary, one being the amplitude of the signal that we send, one being the frequency, and one being the duration of the injection. Why do we call them lines? Because if we send this signal to the duct, then in the FFT plot, we are actually going to see just a huge line occurring. All these parameters that I described are going to be editable in the configuration file of the script. And for each different type of injection, we have some advantages and some disadvantages. The advantages in the case of line injections are that the spectral line amplitude increases with the square root of injection time. Thus, even if we have some areas, some frequencies with low coupling, by increasing the injection time, we can increase the signal and we can actually make that coupling be able to be measured with respect to the noise, the other noise around. Some disadvantages would be that this samples the frequency interval at specific frequencies, and we can miss some artifacts in the coupling function because we don't sample at a particular frequency. So the script has been uploaded to the automatic Virgo process monitor, the VPM. It has a particular configuration file that can be edited by just clicking the link. And once the link is clicked, this configuration file is going to open where we see all the parameters that I mentioned before. We have here a frequency list if we want to input our own frequency list, a duration list, and then an amplitude list where we can specify precisely the amplitude which we want to be injected at each frequency. There are some other parameters that can be modified, such as the channel where we want to send these signals. If we want the script to create an automatic list of frequencies, for example, if you want to start at 10 Hertz and go all the way to 1000 Hertz and then create logarithmically spaced frequency to 20 logarithmically spaced frequencies in that interval, the script can do that. After we modify these parameters, we can simply save the file and run the program by pressing the start button. The code is going to automatically turn on the big coil, send the signal to the DAC. The DAC is going to send the signal to the amplifier. The magnetic field is going to be produced. And the code is going to run for the duration of the whole injection that we specified. Then everything is going to be turned off, including the big coils. Oh yeah, and the process is going to be colored in green once it is running, like we see here for the coils. The result of the script is an output file which specifies the start duration, the start time of each individual line that we injected, the duration of the frequency, and the amplitude. Also in the header of the file, we have specified a quiet time start and an interval, which will be used later on to calculate these coupling functions. We also specify the type of injection. This is also needed to distinguish between them and to calculate the coupling function accordingly, and also the channel which was used to inject this signal. Some example plots. Let me start with the bottom right, where we have two different lines injected, one at 16 Hertz, the pink one at 144 Hertz, the blue one. This is how they show up in the FFT plot. And if we take a look at the voltage produced by the amplifier that is being fed into the coil, we see the variation in the frequency for the two lines. And on the left-hand side, we have an actual line injected in the first plot, and in the middle and bottom plot, we see the line showing up in HREC or in the DARM. So basically, we see the line being measured by the interferometer. The second script we worked on is a color noise injection. This time we send a Gaussian white noise with a specific amplitude spectral density to the DAC. And then we apply a filter to it. We can vary the parameters such as the central frequency of the filter that we want to apply, the bandwidth of the filter, plus minus how many hertz we want to cover, the duration of injection, and also the amplitude spectral density that is being applied. Some advantages for this type of injection are, sorry, I see a chat question. Oh, okay. That we can cover a larger range of frequency as the filter doesn't cut off specifically just around the line. But some disadvantages would be that we cannot increase the spectral amplitude the same way we did with line injections. The process in the Virgo process monitor is quite similar. We have a configuration file which can be edited with a frequency list, a duration list, with the small modifications. Then we need to introduce the bandwidth of each filter that we want to use, since it's a color noise injection. And we need to make sure that the filters that we want to use have been preloaded in the env noise process. So we need to edit, besides the configuration file, we also need to edit the configuration file of the filters of the env noise process to make sure that the filter that we want to use is being added here, and then to save and reload the filters, so everything can be run afterwards automatically. The output file is similar to what we had for the line injection, with the modifications that we also have the bandwidth filter written, and that the type of the injection is going to be color noise now. Some examples, we can also use these filters as low pass filters if we set the bandwidth to start from 0. Basically, if we do the plus minus frequency to go all the way from 0 to a desired frequency, or we can just use them as color noise filters. The third type of injection is the sweep injection, which means that we select a starting frequency, an end frequency, and then we send the same amplitude through each frequency, sweeping the whole range. It is a good advantage because we can probe this way all the frequencies with more energy than we could do with color noise injection, but we only use a limited time for each frequency since we have so many points to probe. I'm going to go a bit faster through this one so we can go to the transfer function calculations at the end and the results. The same configuration file, the parameters, everything that needs to be edited can be edited in the configuration file. And the output file similar to what we saw for the other two scripts. So for the coupling function or transfer function, we use this formula to calculate them, being the difference between the squared of the expected value in the detector, the measured value in the detector, y injection squared, minus the background. And here we use that quiet time interval that I mentioned before, over the same two quantities subtracted for the witness sensors. The witness sensors in this case can either be the Metronis magnetometers or the Partington triaxial ones. We need to set some limits on these fractions. So for example, for the witness sensor during injection and background, we need to have a signal to noise ratio higher than 10 to be considered a proper detection of the injection, such that the injected line, for example, doesn't get confused with other lines that show up in the magnetometers. And for the detector, we use a signal to noise ratio of 2. We use Welch's power spectral density estimate to calculate these transfer functions. Using a frequency peak of 0.025 Hertz for root mean square calculations, an effective time window usually of 100 seconds. We use Han windows with overlap between windows of 50%. This has also been written as a script. Right now it is not present in the VPM, but it could be added to just be run at the press of a button for simplicity. And it takes that as inputs besides the parameter file, which configures the Welch's power spectral density estimation, the outputs of the line injection, the color noise injection, or the sweep injection. And we obtain an output file where all these values mentioned before are being calculated, including the thresholds and the values for the transfer functions, either upper limit if the values obtained for the fractions are bigger than the thresholds, or the upper limits if they're smaller, or the actual measure values if they're bigger. We performed already some lines injections using the automatic scripts. We usually try to inject 20 logarithmically spaced line between around 10 and 1000 Hertz for different durations and different amplitudes, both in the end buildings and in the central building. And here we have the preliminary results. First, for the two end buildings. So we see that the results between the two end buildings and the two different injection dates agree really well. The actual measured values are represented by circles, while the upper limits are represented by stars. Once we reach around 200 Hertz, we notice that there are only upper limits in this region. But so far, so good for this one. In the central building, the results are a bit more scattered. We have, again, two injections for two different dates. Circles, again, represent actual measure values. Stars, they represent the upper limits. We notice just a decreasing trend for the beginning until maybe 100 Hertz, and then an increasing trend towards higher frequencies.
Catalina, sorry to interrupt. We've got about 1 more minute before our next speaker, if you want to summarize.
All right,
And we can
sorry.
follow
Yeah.
up in the chat.
I guess just a couple of slides of comparison between O3 and the results we have now, which we see that they are kind of in agreement for the end buildings, but we cannot really measure them, compare the values, because the location is a bit different between the injections we did in O3 and the injections we did now. For the central building, the difference is a bit larger, but also the location of the coil and the magnetometers is completely different. But overall, we notice that the trend is the same. And just a brief comparison of lines versus sweep. They all seem to agree, but as you see with lines, we do miss the two peaks, the two features noticed in the sweep injection. Thank you. I guess any questions?
Thank you so much, Catalina. So this is great work. We're going to have to move right along to our next speaker. So I encourage you, if you have questions for Catalina, I certainly do, to please follow up in the chats and prepare yourself for that, Sofia. So you might see some questions popping in and out of the chats. And our next speaker. So Sofia is going to be telling us about GSpyNetTree, a signal versus glitch classifier for gravitational wave event candidates. Let's please welcome Sofia Alvarez and take it away, Sofia.
Thank you, Jess. Yeah, hello, everyone. I'm Sofia. I just finished my undergrad at Uniandes in Colombia. I've been working with the UBC group in Justice group, actually, at UBC for a year now, and I'm an incoming grad student at MIT. And today I'm going to talk to you a little bit about GSpyNetTree, which is a signal versus glitch classifier for gravitational wave event candidates. So, yeah, just to kickstart a little bit, we have 4 detectors for O4, LIGO Hanford, LIGO Livingston, Virgo, and Cadre. However, online at the moment, we just have LIGO Hanford and LIGO Livingston, which are the ones I'm going to focus on this kind of presentation. So, yeah, most of you know what glitches are, but just a quick review. They are non-Gaussian transient noise measured by gravitational wave detectors. They result from instrumental, environmental, or unknown sources, and they come in various time frequency morphologies. However, glitches are very challenging when they mimic the actual form of real gravitational wave events, because they may generate false positive candidates, which is very challenging for electromagnetic follow-ups. They corrupt data, and they bias astrophysical parameter estimation. In previous observing runs, we've been using GSpy, which is a great tool. It is a multi-class convolutional neural network image classifier that distinguishes various different glitch classes and one chirp class. So as many of you might know, chirps are hardware injections that emulate gravitational wave signals, and GSpy distinguishes between glitches and chirps using spectrograms, which are time frequency visualizations, just like the one shown on the right. Yeah, GSpy was super successful in glitch classification in previous observing runs, and thanks to GSpy performance, we saw the potential to use it to use its architecture to build a gravitational wave signal versus glitch classifier, which we call GSpyNetTree. So the importance or the necessity of GSpyNetTree is that LIGO detectors are more sensitive than the current observing run that's going on right now. So we need further automation of candidate event validation. What we want to do with GSpyNetTree is basically to detect glitches responsible for or in the presence of gravitational wave candidates in order to inform event candidate validation for the data quality report of LIGO Virgo. So in order to build this gravitational wave signal versus glitch classifier of ours, we first start with this basis. We noticed from previous studies that there is a huge effect of math on time frequency morphology of gravitational wave candidates. And basically, depending on their total mass, some gravitational waves are going to be more morphologically similar to certain types of glitches than other types of gravitational waves. So we can see there are 3 total mass ranges for candidate events: low mass events that go from 5 to 50 solar masses, high mass from 50 to 250 solar masses, and extremely high mass candidates from 250 to 350 solar masses. And yeah, so here's just this difference I was talking earlier about. Here on the left, we have some gravitational wave examples, and on the right, some other glitch examples. So for instance, let's see the third line over here. You see a high mass signal on the left, and then on the right, you see a empty glitch. And as you can see, they are very morphologically similar. And this is exactly what we aim to address with GSpyNetTree, being able to distinguish between these gravitational waves and glitches that are morphologically similar. So as I said, well, GSpyNetTree, it's an abbreviation for what we call GSpy convolutional neural network decision tree. And based on these 3 mass ranges that we have, we build a decision tree sorted via total gravitational wave candidate mass, which is made up of just 3 gravitational wave signal versus glitch classifiers, 1 for each of the mass ranges that we consider. So we have low mass, high mass, and extremely high mass CNNs, each with morphologically similar glitch classes that we found from GravitiSpy. In the case of the low mass CNN, we also include a very saturated glitch, which is called koi fish. It's this one over here in D. And we used to just account for very saturated glitches that may happen in the low mass regime. And then for the 3 classifiers, we also include scattering, fast scattering, and low frequency lines, which were the most common detector glitches, as I'll just mention in a few seconds. So basically, our CNNs all have, well, the training sets of our CNNs all have a subset of all of these glitches, except for F, G, and H, which are shared among our 3 classifiers. In the case of low frequency lines, it's because they were very common in O3 Virgo and during the 15th engineering run. And in the case of scattering and fast scattering, it's because they were the most common glitches in O3, and they were identified in broad ranges of beta time. So we just wanted to be robust against this kind of glitches that are very common or very current and like them Virgo detectors as well. So yeah, in order to build our O4A version of GSpyNetTree, we implemented some tactics in order to make it robust against a broad array of different scenarios. So first of all, we wanted to make GSpyNetTree robust against a broad array of background noise. So in order to address this, we use data that, well, just normal LIGO data, also implemented data with some calibrations. And we also use data both from LIGO and Virgo to account for different background noise that may happen in both detectors, and just to be, robust against everything that, a lot of scenarios that could happen. We also want to make robust against incoming gravitational wave signals with different orientations, not only optimal latitude and longitude, and also we wanted to be robust against overlapping gravitational wave signals and glitches. And I want to emphasize a little bit in this last point, because in previous studies that we did with GSpyNetTree, we noticed that when there was a glitch happening in close proximity of a gravitational wave, more than 60% of the gravitational wave signals, and actually 7% for the high mass regime, were misclassified as glitches. And this is very super undesirable because this may lead to unnecessarily vetoed candidates. Actually, in the 3rd observing run, it already happened with 24% of candidate events that overlap with 1 or more types of glitches, and it is very expected to happen during O4 because we have an expected event rate of 1 gravitational wave candidate per day. If you go to GraceDB, you're gonna be able to see that we are having a lot of candidate events. All right, so here are some samples of this, like different time offsets we use between gravitational wave signals and glitches. So they are different for each of the glitches. We just wanted to make sure that we were robust against anything that could happen, a glitch happening very close to the gravitational wave, or maybe a little later, or a little previously because it's before the gravitational wave happens. Okay, so then we proceeded to build this training set of GSpyNetTree. Here is like a sample of what a sample of GSpyNetTree looks like. For those of you who are familiar with GravitiSpy, you may see a lot of similarities here. It is basically, I think it's the same sample. So we have 4 spectrograms for time frequency visualizations, 0.5, 1, 2, and 4 seconds in duration, and these are arranged in a 2x2 matrix. Well, I included the image on the left just for reference, but we used the ones on the right to train our CNN in order to avoid the redundancy of the 3 RGB channels and also to reduce the number of parameters of our CNN. And well, we just grabbed more than 1,000 samples per glitch class per classifier, including data from all LIGO and Virgo detectors. We have 1,800 samples of overlapping gravitational waves and glitches, and we also have 1,800 samples of only gravitational wave signals. Unfortunately, our only misrepresented class is the low frequency lines class because we could only manually verify around 300 samples of those before O4 started, but we're working on that right now. Okay, so we also wanted to change a little bit to GravitiSpy's architecture for GSpyNetTree. So we built a multi-label architecture, as I'm going to explain right now. So some classifiers, as GravitiSpy in the previous version of GSpyNetTree, we have this in a paper right now. You can find it in the archive. Yeah, so multi-class classifiers are only able to predict one type of glitch class. And yeah, just they can only predict one type of, they can only predict one class because all of the probabilities of the classes have to add up to 1. However, we can also find multi-label classifiers that are able to predict 0 or more classes, because instead of all the probabilities adding up to 1, each class separately is assigned a probability between 0 and 1. And if the probability is above 0.5, then it is said that that class is going to be predicted for that specific sample by the CNN. So we wanted to use a multi-label classifier because, as you can see, we can predict gravitational waves in the presence of glitches, and we're not gonna lose either of them when we train or when we test our CNN. And in order to do this, we also changed a little bit the machine learning architecture of GSpyNetTree. I'm gonna go a little fast about this, but instead of using the original GravitaSpy architecture, we used Inception v3. So Inception v3 is one of the state-of-the-art CNNs for image classification tasks. And while it is a very deep network with a lot of convolutional layers, it was the one that gave us the best results overall. When we tested different CNN architectures, and it has shown also state-of-the-art accuracy on many training sets. So yes, now let's dig a little into our GSpyNetTree results. And well, so for the purpose of GSpyNetTree, the most important thing is to detect a glitch responsible for or in the presence of a gravitational wave candidate. And along with other tasks, GSpyNetTree is part of the LIGO Virgo data quality report. So basically, GSpyNetTree assesses or informs if a gravitational wave candidate should be predicted or not by, should be confirmed or not by LIGO. So while not desirable in this scenario, a glitch misclassified as another type of glitch is okay, because both mean that those are data quality issues. And while not desirable to, a gravitational wave misclassified as a no glitch is okay as well, because both mean that no data quality issue was identified. We want to avoid at all costs a glitch misclassified as a gravitational wave, which would be a false candidate. This is not a huge problem in O4 because these are going to be flagged by humans, but the one that we want to avoid the most is a gravitational wave misclassified as a glitch, or where no glitch is found, which means that a data quality issue was missed. These are the results for our classifier: low mass, high mass, and extremely high mass. For the high mass classifier, this was the one with the best results. The low mass classifier had around like 10% of gravitational waves classified as no data quality issues. And for the extremely high mass classifier, we had around 5% of data quality issues misclassified as gravitational waves. But overall, just to give you a quick overview, more than 96% of our data quality issues were identified in all three classifiers. And most of the cases of misclassified data quality issues were low frequency lines, but as I said, we are addressing those and trying to improve them. More than 90% of gravitational waves no glitch samples are correctly classified. We also plan to improve this, finding an optimal time frequency spectrogram wavelet basis. And we also found that our false alarm rate is very low in the entire mass range. The one that showed like a little bit of trouble was extremely high mass classifier. And this is due to the fact that gravitational waves and low frequency blips are very similar. So in order to address this, we plan to include the Mercator projection that we have used in previous studies, because with this Mercator projection, the signals are stretched up in frequency, and you can see that you're more able to extract features of the samples with the Mercator projection applied than before. And yes, that's why we decided to include the Mercator projection for a future iteration of GSpyNetTree. And yes, just a little fast, I'm not sure how much time is left, but GSpyNetTree lives in the DQR. As I mentioned, the DQR is a data quality report, which is LIGO Virgo software that consolidates and packages results used in event validation pipeline. So yeah, just a little bit about how the DQR works. When a new gravitational wave candidate is detected, it is stored in GraceDB. Then LV broadcasts and notice to all subscribers, which includes the data quality report. The data quality report triggers all the analysis and its tasks, including GSpyNetTree. And then GSpyNetTree will respond to the data quality report with a web page and then this web page is going to be published again in GraceDB. And then humans will be able to assess if this candidate event should be retracted or confirmed. When that event gets into GSpyNetTree, first of all, we get the strain data, and then we generate the spectrograms for that strain data. And depending on the mass range of the event, it is going to be sent to either of the classifiers, so low mass, high mass, and extremely high mass. And with that, we're going to get the prediction of GSpyNetTree with the probability that the event is a gravitational wave or a glitch. Here are two samples of GSpyNetTree. This is from O2. On the left, there is a gravitational wave where no data quality issues were identified. And on the right, there's a fast scattering glitch. And as you can see, both of them were accurately predicted by GSpyNetTree. You can see these examples and more information in GSpyNetTree on that link above. And yeah, so in the current observing run, GSpyNetTree has played a great role identifying candidate events which have been retracted. 2 of them were retracted due to non-instrumental artifacts, and both types of glitches were correctly identified by GSpyNetTree. We also found that some candidate events were misclassified as no glitches. As I said, this is not problematic, but we are working towards better distinguishing gravitational wave candidates from actual no glitch events. And yeah, just for future work, we plan to include more low frequency line samples in the training sets of GSpyNetTree. We also plan to obtain the optimal time frequency spectrogram wavelet basis per classifier to maximize the classification of gravitational waves that are misclassified as no glitches. And then we also plan to include the Mercator projection for the extremely high mass classifier to better distinguish between gravitational waves and low frequency blips. We're also developing a clustering tool in which what we want to use this for is that we want to put here the incorrect classifications of GSpyNetTree and see how they cluster to see if for some reason they generate a new cluster. Maybe it's a new glitch. And if it is a new glitch, which I'm gonna show this here, yes, so if there are like many events that, that are very similar to this new glitch, we can contact that to our instrument people to see if there's something that could be done on the detectors, if there's nothing that can be done in the meantime, if this glitch is very common or morphologically similar to some kind of the gravitational waves from the mass ranges we have, we could add this new glitch class to GSpyNetTree, and this way GSpyNetTree would be robust against new appearing glitches during 04 and onwards. And yes, thank you very much for your attention. I hope you enjoyed this talk.
Thank you, Sophia. So we have a few minutes for questions. So if you have a question for Sophia, I encourage you to type it in the chat window. We can also try raising hands. And while people are thinking about it, Sophia, I wonder if you could tell us, what do you think the most important improvement is going to be for GSpyNetTree performance moving forward?
Yeah, so I think that the most important thing that we should be addressing with GSpyNetTree would be including, first of all, including more low frequency line samples, but at the same time, yes, also finding the optimal time frequency spectrogram wavelet basis for each of the classifiers, because yeah, I mean, we don't want to lose our gravitational wave signals, confused with no glitches. So I think those 2 are the most important.
Great, thank you. And I see Chad has a question. Chad, would you like to voice your question, or shall we read it?
Let's see if that's my question. Okay. Yes, my question is, are there any points when you're doing these tests in your parameter space, like for example, edge-on inclination, that are particularly difficult for distinguishing glitches from signals?
Yeah, good question. Thanks, Chad. Well, when we simulated our signals, and then we first were considering just the optimal parameters of the gravitational waves, and then simulated with just random parameters, we didn't notice a lot of differences in our simulated signals compared, in either cases. So it was not that, I think it didn't play like a huge role. There was nothing that was like highly, that made more difficult distinguishing between them.
Well, I will take the opportunity to follow up on Chad's great question. What kinds of noise does GSpyNetTree find the most challenging to differentiate?
Well, good question, Jess, thanks. So first of all, I would say that low frequency blips, especially in the extremely high mass regime, are the most difficult ones, but those are to distinguish between gravitational wave events and glitches. Right now, at the moment, GSpyNetTree is having some trouble distinguishing low frequency lines. It is actually misclassifying a little bit of them with no glitches. I guess this is because it is maybe in the low frequency regime, and as well as because it was underrepresented in the training set. And as we were using a very low Q value, maybe that also has an effect on how they were appearing to GSpyNetTree. If we were using like a non-optimal Q value, that would mean that maybe the samples would be very faint, I'm gonna say, and what would be like very easy to confuse with no glitches. So I'm gonna go with those 2.
All right, we've got 1 more minute and 1 more question. Johan, would you like to voice your question?
Yeah, I would just like to ask, what waveform model are you using to generate your signals for the training data set?
Yeah, we use IMR phenome V2.
Oh, so that only includes the dominant mode, I presume?
Yeah.
Okay.
Yes, and just CV2 signals, we don't include burst wave in our training set.
All right, thank you again, Sofia. Thank you also, Catalina, and thanks everybody for some great questions. So now it's time for a 10-minute break. So we're going to reconvene back here 10 minutes after and get started with our next talk by Meg Millhouse. All right, thank you, everybody. I hope you have a good break and the chance to grab some caffeine. And we'll see you soon. Hello, everyone. Welcome back. So our next talk will tell us about separating instrumental glitches from generic signals in gravitational wave data. So let's welcome Meg Millhouse. Please take it away, Meg.
Thank you. Cool. So today I'm going to talk about separating instrumental glitches from generic gravitational wave signals in LIGO data. I'm working on this with an undergraduate, Jacob Paris, and I'll highlight work from some other folks throughout as well. So starting out with just a brief recap of LIGO, Virgo, CAGRA observing runs to date. There have been 3 complete observing runs, and in each run we've seen signals from brand new types of sources. So of course, in the first observing run, we saw the very first gravitational waves from a binary black hole. In the second run, we saw the very first binary neutron star merger in gravitational waves. And in the third observing run, we saw the first neutron star black hole binaries. And as we observe longer and our detectors get more sensitive, we can hope to see brand new types of transient signals, just like we've been seeing new flavors of these compact binary coalescence events. Some proposed sources include core collapse supernovae, the post-merger emission from a binary neutron star merger, cosmic strings, and of course, there could be signals that we haven't yet predicted at all. And it's important to note that not all of these signal classes are well modeled, so we can't always rely on templated searches or traditional parameter estimation techniques. One challenge in searches for these novel type of signals is the presence of non-Gaussian transient noise artifacts, or what we call glitches, which probably know all about now. Glitches occur in detector data at about once per minute. They come from a variety of sources, both known and unknown, and a wide range of morphologies in time frequency space. So here's just a few examples of spectrograms of some different glitch classes. And because glitches are fairly frequent, glitches sometimes happen temporally close to actual gravitational wave events. So for example, the spectrogram on the right shows GW170817, the first binary neutron star merger, that nice in spiral track there, with a large obvious glitch right in the middle. In total, about 20% of the events from the last 2 gravitational wave transient catalogs have had glitches nearby. And one big concern is that the presence of glitches could bias parameter estimation of event. So there are a number of glitch mitigation methods that exist in order to avoid that bias in parameter estimation. In the future, if LIGO and Virgo do detect a novel signal class, it's going to be crucial to learn everything we can about the signal, including its time or frequency domain waveform. So in this work, we investigate our ability to reconstruct a signal for which we don't have a model and where there may be a glitch nearby. And I'll emphasize that here we're not really discussing the detection aspect, but rather how we might follow up an interesting candidate and sort of assess our readiness for understanding potential novel gravitational wave detections. There are a number of different methods for searching for and reconstructing generic gravitational wave bursts. In this talk, I'll be focusing on an algorithm called phase wave, which can reconstruct both gravitational wave signals as well as instrumental glitches with minimal prior assumptions on these morphologies. Phase wave uses Bayesian inference and a wavelet reconstruction. So we use a sum of sine Gaussian, also called Morley-Gabor wavelets, to reconstruct gravitational wave data. And each wavelet's uniquely defined by 5 parameters, so central time, central frequency, quality factor, Q, as well as an overall amplitude and phase. And this gives their location and shape in time frequency space. And we marginalize over these parameters using a reversible jump or transdimensional Markov chain Monte Carlo, where the number of wavelets itself is a parameter in the model. So it's a clever way of letting the data decide for itself how complicated the model needs to be. And here's, sorry, one second. Here's an example of phase wave in action on the very first gravitational wave event, 1509-14. The left plot shows one draw from the posterior. So just sort of one snapshot in the chain. The top plot is the individual wavelets as they are at that point in the chain, and the bottom is how they sum together for the full waveform. And then on the right, this is the full posterior distribution. So this is a Bayesian analysis. So we get a full posterior distribution of what we think that waveform is. So this is basically like a 2-dimensional histogram. And phase wave has a couple different models for what could be in the detector data. The first is the signal model, which says that the data contain a real astrophysical signal. For this, the parameters in our model are a single set of wavelets and some extrinsic parameters like the sky location, which tell you how each detector will respond to the signal. So you take your wavelet sum, combine it with like the antenna pattern, and it tells you what the signal should look like in each detector. And for this projection onto the detectors, we have 2 different polarization models. The first is elliptical polarization, where the plus and cross components of the gravitational wave are related in this way by this parameter epsilon. And we have a newer, more generic polarization where we use a different set of wavelets, each for the plus and cross polarization that have some common parameters, but then also some differing parameters. Next, we have the glitch model, which says the data contain an instrumental glitch. And in this case, the reconstruction is independent in each detector, since we expect a true instrumental glitch to be uncorrelated between instruments. Well, the original incarnation of phase wave assumed disjoint signal and glitch models, meaning we assume the data contain either only a signal or only a glitch. A new development described in our 2021 paper allows for the data to contain both a signal and a glitch, or in other words, it simultaneously models the coherent and incoherent power in multiple detectors. The main use and purpose of this so far has been to remove glitches from around gravitational wave events prior to parameter estimation. There have been a couple studies about the effectiveness of this glitch subtraction and also the methodology. There's a paper in PrEP led mainly by Sudarshan Ganj, Joshua Brandt, and Jack Sullivan that used this joint signal and glitch model to subtract different classes of glitches around simulated binary black hole signals and showed that the parameter estimation for a lot of cases is improved, as well as the overlap between the injected and recovered signal. And they also introduced separate priors for the signal and glitch models. And then Sophie Howrahan et al. Worked on replacing the wavelet signal model with an actual compact binary model. They used IMR phenom-D. And this can further improve the safety of glitch subtraction for parameter estimation. So you still use the wavelets to model the glitch, but you assume that there's a compact binary in the data as well. So now moving on to non-CBC-like signals. So like I said, what we investigate in this work is separating glitches from signals for which we don't have robust models. And for this, we're going to use a waveform class that has previously been employed to test unmodeled searches or signal agnostic searches, these so-called white noise bursts. These signals are excess white noise limited in time and frequency. Here's an example of a white noise burst in the time domain, the Whiten strain, as well as a spectrogram in time frequency domain. So these symbols, don't have the nice sort of smooth frequency evolution of compact binaries. So they're a bit more complicated, and they're not something you can find with like a match filter search. And these aren't based on like a real astrophysical model, but are instead stand-in for a sort of totally unknown surprise signal. For compact binary signals, past studies have tested glitch and signal separation via parameter estimation, but because we're looking at signals without templates, we don't really have an exact equivalent to parameter estimation. So right now for our figure of merit, we're going to use this quantity called the overlap. The overlap is defined here. These parentheses denote the noise-weighted inner product. And the overlap compares two different waveforms, and it ranges from 1, which is a perfect match, to -1, which is perfect anti-correlation. The overlap depends on a number of different things, such as the specific morphology of the signal, as well as its signal-to-noise ratio. The plot here shows an example of the overlap versus SNR for some white noise bursts in a previous phase wave study, just to give you a sense of sort of how that evolves with SNR. And onto the sort of full test data set that we'll be using. For now, we're going to use those white noise bursts as the signal model and inject those into data that contains blip glitches. We chose some blip glitches from both the second and third observing runs. And in this case, we are using Hanford and Livingston data, but there's only going to be a glitch in one detector at a time. The white noise bursts have central frequencies of 150, 300 hertz so that they overlap in frequency with the blip glitch. We inject the white noise burst somewhere within 0.2 seconds of the blip glitch. So here's some spectrogram examples of the signal and glitch separated by little time on the left and right, and then in the middle when that glitch and signal are right on top of each other in both time and frequency. And for results, I'll start by showing just one example of a single phase wave run using that joint signal glitch model. And this is one where the signal and glitch are right on top of each other. And in this case, the glitch is in the Livingston detector. This is the time domain reconstruction of the signal. So the purple is the phase wave recovered signal model, so looking for the coherent power. The shaded bands are the 50% credible interval. The gold is the recovered glitch model. And the teal, if you can see it, it's a little bit hard to see, is the injected signal, sort of the true signal, and the light gray is just the full data. So there's no glitch in the Hanford data, so you just see a nice flat line for the recovered glitch model, but you do see the signal model following this injected signal pretty well. And then in Livingston, where we have this loud blip glitch, you see the glitch model picking up that power, while the signal model still follows the injected signal pretty closely. So doing a pretty good job at separating that signal and glitch power. And looking at something similar in the frequency domain, so Fourier transform of the previous slide, again, you see that separation of signal and glitch. And just for interest, these are the histograms of the number of wavelets used in each model. The signal model tends to use about 6, 7 wavelets to reconstruct that white noise burst. The glitch model mostly uses 0 wavelets in the Hanford detector where there is no glitch, and uses 2 or 3 wavelets to reconstruct that blip glitch in Livingston. And quantifying this a bit more, we can look at the posterior distributions of the overlap between the injected and recovered signal. So for the signal model on the left, we get an overlap of around 0.75, which is pretty consistent with what we've seen with previous white noise burst studies. And then for the glitch model, oops, sorry, I forgot the labels here. So signal on the left, glitch on the right. So for the glitch model, the overlap tends to be around 0, which in this case is good because it means the glitch model is not picking up a lot of the signal power. And now looking at a whole collection of events, we can look at the overlap as a function of the injected signal to noise ratio. The blue are for data that contain both a simulated signal and a glitch. And the orange is data where we inject a signal into the data and there is no glitch near the analysis window. So it is still real data, just not data containing a glitch. And we see that for the most part, phase wave can do equally well at reconstructing unmodeled signals, whether there is or is not a glitch nearby. So that's encouraging. It means if we do get some sort of novel signal, right now we're pretty confident we could reconstruct the true waveform, even if the data is glitchy. But of course, there are some outliers and exceptions here where we are doing significantly worse in glitchy data. And I'll just highlight one example of those. So again, this is the time domain reconstruction. Again, we have a glitch in Livingston here, and you see the signal model is picking up a lot of the glitch power. And this can happen sometimes for very loud glitches like this, where it's loud in one detector. The likelihood can find a very small region in the sky location parameter space that allows for a huge SNR disbalance in the two detectors. And then it can have a little bit of trouble moving away from that region of high likelihood. And just an example again of that overlap, where for the signal and glitch model, you see both are getting like a moderate amount of the signal power. So in this case, it's the glitch model is making up for some of the signal model by latching on to that white noise burst. So some further investigations into these cases, we can look into adjusting the priors to not get stuck in those weird parameter space sky locations, or perhaps change some of the chain mixing or initial burn-in procedures to better explore that parameter space. Yeah, so in summary, glitches could be particularly challenging for unmodel analysis methods. If we get some sort of novel signal, we really want to be sure that we can learn all about it and reconstruct that waveform. Right now, it looks like Phasewave can faithfully reconstruct most generic gravitational wave signals that coincide with glitches. And for future work, we're going to look at more glitch classes, more signal classes, and maybe investigating some of those priors. And that's all I have. Thank you. I think I'm pretty much on time.
You are exactly on time. Thank you so much, Meg. So we have plenty of time for questions. So I encourage you, if you have a question, to please either type it in the chat window or raise your hands. And while people are thinking about it, oh, I see we have a question from Zach. Please go ahead, Zach.
Thanks, Jess. Meg, that was a fantastic talk. Thank you so much. I was curious if you could talk a little bit about the injection procedure for injecting the white noise into the time series with the blip glitches, and really if that was difficult, or if you had a strategy for that.
Yes, it was surprisingly difficult. So I thought I could use a fancy time slide method, but let me see if I can go back to, oops, sorry. Yeah, so what I ended up doing is a lot of these burst injections, we call them in LIGO land, are in GWF frames. So I made a GWF frame for like a white noise burst or a couple white noise bursts, and then you have to make it for a specific time, and then I just remade it at various times, along a known blip glitch. So it's a little bit of a pain, but yes, so it's using the sort of burst style MDC machinery, if that makes sense at all. You can follow up offline if you have more questions. This is it's on the, yeah, I can share the repository that does this too, if you are interested in it at all.
Very nice. Thank you very much for the question, Zach. So while others are thinking of their questions, I have a question for you, Meg. So you mentioned that detection is not the focus of your current work, but do you think this method could be incorporated as part of a detection pipeline?
Maybe. So Phasewave itself is full MCMC, which is a little expensive to be a full search. So we would not be running on just the full stretch of data. But as a follow-up to sort of further assess detection confidence, yes, I think that could be a method. I do want to look at sort of like the Bayes factors for the signal plus glitch and signal only model at some point, but I haven't gotten all the way there yet.
Okay, very interesting. Thank you. All right, let's see. We have time for one more question. Does anyone else have any questions for Meg? I suppose I'll take the last one for myself. What are you the most excited about in terms of future developments for Phasewave?
For Phasewave? For future developments, I think when we get more detectors online, when Virgo comes back online and Catalina comes back online, it will be exciting to see how adding more detectors can make things better or worse, and whether we could get, much better glitch rejection, or whether it will hamper us a bit. Yeah, I mean, hopefully a brand new type of signal would be exciting too for Phasewave, but keep our fingers crossed for that.
Yes, agreed. That would be tremendous. All right. Well, thank you so much, Meg, for a great talk. And our last talk of the session today, so characterizing the responsiveness of the GstLAL search pipeline to gravity spy glitches, we have Zach Yarbrough. So please take it away, Zach.
Hi, everyone. My name is Zach. I'm a graduate student at Louisiana State University, and I'm really excited to share with you today our work about characterizing the responsiveness of one of our search pipelines to glitches classified by the Gravity Spy convolutional neural net. To begin, I'd like to start with the broad question that some of my colleagues who have gone earlier in the session have done a fantastic job of introducing, which is what is a glitch? As you've heard earlier, a glitch is by definition a non-Gaussian short duration noise transient. That's a bit of a mouthful, so we tend to just refer to them in the collaboration colloquially as glitches. These undesirable noise sources can be caused by a variety of factors, some known, many unknown, but that can include the instrument itself, the environment around the instrument, and of course the interaction between the two, such as ground motion caused by earthquakes or human activity, winds tilting the corner station, beam tube in station, the scattering of light from the beam path off of a reflective surface and then back into the beam path, and many, many more, some of which we still have yet to pin down exactly. Some examples of these glitches are shown on the left. We have a koi fish, a whistle glitch, slow scatter, and extremely loud. And these are all categories that these are placed into by the Gravity Spy convolutional neural net. It uses normal image recognition to convert these frequency morphologies into categories so that we can analyze them more granularly. Some of the names are for the names of these classes are for their sources. For instance, there's an air compressor glitch that we know to be usually correlated with the turning on and off of an air compressor on site. And some are just a little more fun, such as a koi fish glitch, which is very, very similar to like a top-down view of a koi fish in a koi pond. Similarly, a whistle glitch starts high in frequency, dips low, and then returns to its original frequency, very similar to a whistle produced by a human. These are really the bane of the existence of many an LVK member, and certainly many a graduate student in particular, because these glitches cause us a lot of issues. Sometimes when presenting this work, we get asked why do we care? And as some of the earlier talks introduced, these glitches provide a number of different issues. So we're really interested in mitigating them. Not the least of these issues is the fact that they can mask or mimic gravitational wave signals. Shown here is gravitational wave 170817, the only electromagnetic counterpart that we have observed to date. I should say the event with an electromagnetic counterpart that we have observed to date. You can see the chirp signal here from the binary neutron star, much longer than the traditional vanilla BBH. And then around the coalescence time, we have this really, really powerful glitch that for my money looks a bit like a koi fish, maybe a tomte. And this glitch really did mess with the analysis that the processes that we trust to return positive identification for gravitational wave candidates. Additionally, 80 public notifications were sent out during 03, and 24 of those events later had to be retracted after advocate follow-up, after finding out that these were in fact not actually caused by gravitational waves, but rather from noise signals in the form of glitches. We've had one retraction thus far in 04, which is fantastic. We are ahead of the curve for 03, but these problems present themselves quite frequently. The masking of gravitational wave signals or the mimicking of these gravitational wave signals to the eyes of our pipelines. Now, these search pipelines, live on computer clusters and are running 24/7 to search for gravitational waves, but they're not perfect. And sometimes they can be fooled. And because of that, we want to understand how these glitches manifest in these pipelines. What do the pipelines see? How do they react to these different glitch types? So we can better defend against glitch impactfulness and maybe develop some protocols for mitigating the risk presented by glitch types. So for the scope of this talk, we're going to be discussing the GstLAL pipeline and how it responds to a variety of different glitch types over 1 week of data in 03. To do this, we need to associate glitches to the triggers that they cause. Sometimes this can be done somewhat easily with the parameter from GstLAL like signal-to-noise ratio. Shown here is an extremely loud glitch on the left and a scattered light glitch on the right. And then each of these bars represents a trigger, showing the signal-to-noise ratio of the triggers. For the extremely loud glitch, we see one trigger that has a much higher signal-to-noise ratio than the ones around it, clearly leading us to believe that this trigger here in the middle at about 42.5, maybe 43 seconds, is indeed caused by the extremely loud glitch. Unfortunately, in other situations, such as with scattered light, many of the triggers don't align so well in time and also don't stand out nearly as much in parameters like signal-to-noise ratio. So here, we can't do really any definitive analysis on which trigger or triggers, plural, is caused by the scattered light glitch. To get around this, we developed a global likelihood ratio that quantifies how likely it is that a given trigger is caused by a glitch. We call this value the von Schweetz value, and I'll hereby refer to that as the VSV. The mathematical definition for the VSV is a bit beyond the scope of this talk, but we show its performance here on these same glitches that were shown on the previous slide. You can see with the extremely loud glitch that the same trigger with a high SNR is represented well by the VSV, a high likelihood of being caused by the glitch in question. And then similarly for the scattered light glitch, these likelihoods for the scattered light glitch are greatly reduced, kind of creating a sort of effective background or low likelihood, low impactfulness, if you will, of these triggers as a result of this glitch. So this is the tool that we'll be using for the rest of the talk to associate the triggers caused by specific glitch types. So here's the distribution, the number of glitches for the week in question of O3 data. And we do this for both detectors. Shown here is Livingston. And one thing to keep in mind as we go through the rest of the talk is the presence of tomte glitches. Tomtes are kind of a sloping triangular shape, mimicking a tomte hat of Nordic origins, I believe. Fun little detail. But this is the number of triggers, the number of glitches, excuse me, that we'll be working with as we go forward. So the first step in our process was to calculate the VSV for each of these glitch types and the triggers around them during this week of data. And we show that histogram here. So we can clearly see four distributions, four different peaks, if you will. And the majority of each of these peaks, the first one here at a low VSV, a sort of a middle VSV, and a very high value, are caused by different glitch types. The best example of this is this middle peak around 0.6 that happens to be caused by tomtes. We did this kind of broad visualization of this, a broad perspective, if you will, of this week. So we can impose a cutoff for each detector at around 0.18 for Livingston and 0.2 for Hanford. We did this because we really want to concern ourselves with the triggers that are very likely to be caused by glitches. We saw earlier that scattered light glitch produced a lot of triggers with VSVs lower than 2, and I spoke briefly about that kind of effective background. So we used this first distribution to create this cutoff, that 0.18 or 0.2, to be the 90th percentile of this first distribution, so we can really focus on these high likelihood triggers that are very likely to be caused by glitches, so we can really analyze their parameters, so we can understand why, in particular, these glitches are causing triggers that present themselves in the GstLAL pipeline. So once we do that, we can break it down into individual parameters. Shown here are histograms of signal-to-noise ratio and mass total, just interesting parameters that are produced by the GstLAL pipeline. And then the bar plots behind the histograms show the percentage of that histogram bin caused by a given trigger type. So here at around an SNR of 300, we see about an equal 50-50 contribution for both extremely loud, this dark orange color, and koi fish, this lighter orange color. From this, we can draw a number of interesting conclusions. Specifically, above a high SNR cutoff, around 100 in this figure, it varies from detector to detector, but we really see the presence of a few really strong, powerful glitches. Specifically extremely loud koi fish, and in the case of LIGO Livingston, tomtes as well. Similarly, we see a really big contribution from scattered light at low SNR and throughout the region of total mass, and as well as a pretty sizable contribution from blip, that's fast scattering here between about 10 and 90 signal to noise ratio. So really, this was our proof of concept when we started this project. We want to see, are there different contributions? Are there noticeable trends at different parameter spaces, parameter values that are specific to glitch types, so that we can maybe focus on a specific one, a really impactful glitch type, a really dangerous glitch type. And this kind of shows that high SNR triggers in this week were shown to be, for the most part, almost exclusively koi fish and extremely loud glitch types at LIGO Hanford and Tomtes and LIGO Livingston. So going further, we can visualize this in a kernel density estimate that produces these unique distributions between glitch type and detector. We were really happy to see unique distributions here, just to show that there is indeed a difference. There is indeed different contributions at different parameter values, such as for scattered light, we kind of have this island here at a higher mass when that disappears for the extremely loud glitch type. This was our first steps in developing what we hope to be a tool used as a data quality check. The figure here on the right shows a mass 1, mass 2 KDE for koi fish glitch type caused triggers for LIGO Livingston. And then the red X's are retracted triggers from the third observing run. And we see a great deal of overlap between the characteristics of the glitched triggers, if you will, and the triggers that had to be retracted after advocate follow-up. You'll notice that it doesn't capture all of them, which is not to be expected at all. This is every retracted trigger. We have not gone back and analyzed which triggers, which glitches were responsible for these retractions, but we can see a big overlap with just this one glitch type. So as you can imagine, future work will be involved with breaking this up further into different glitches to see maybe we can cover all regions of parameter space by combining these estimates of parameters. But as you can imagine, we were very happy to see overlap between these retracted triggers and the parameters produced by these glitch triggers as well. So next, we visualize the same data in parameter spaces relevant to GstLAL. Again, here's our mass 1, mass 2 plot. And we can see that in the high BBH region, the high mass BBH region, we're really dominated by Tomtes. This is LIGO Livingston, and this is LIGO Hanford here. We expected this. The number of Tomtes at LIGO Livingston is truly daunting and, kind of makes the average DetChar expert a little bit sad when we think about it. But we are really happy to have this valuable information. Because if a trigger were to come back in low latency with mass 1 of 100 and mass 2 of 30, that places it in this Tomte region. And hopefully our future analysis can quantify this better, and we can say, okay, you fall within this Tomte region, and we now have a statistical measure or an analysis procedure that allows us to quantify indeed how likely it is that a Tomte caused this trigger. Similarly, this is a plot really relevant to GstLAL. This is a background plot, and we expect gravitational waves to appear in this parameter space with low chi-squared and high SNR. So honestly, really just this region, this light orange koi fish region. This is where we expect gravitational waves to appear. So having this information is really valuable. We can see that scattered light glitches, this kind of indigo here, does not present as big of a threat to this really high value region, this gravitational wave region, as a glitch type like koi fish or extremely loud or Tomte. So this was the first time we've been able to connect analyses like that, a kind of marriage between CVC searches and detector characterization that we're quite happy with, and information that has been passed on to both working groups and that we are continually building on to try to further our understanding and build our intuition to how these things kind of work together so we can better protect ourselves against retractions and against the impactfulness of glitches. So for some preliminary conclusions using these two plots here, we can see that pattern of extremely loud and koi fish glitches occupying that gravitational wave region here with low chi-squared, high SNR. We see low frequency lines dominate the high mass NSBH region here. Blip glitches contribute widely to the middle ranges. Tomte glitches are really everywhere. And then the scattered light glitches make up the majority of triggers in both LLO and LHO. We also see that some MAS1, MAS2 regions tend to be less sensitive than others. So these will be regions for follow-up. What is it about these particular parameters that make them less susceptible to being impacted by glitches than something like, a high mass binary black hole? Similarly, these KDEs show unique distributions per glitch type and per detector. And this is a promising point of progress for a data quality tool, being able to do this in follow-up to, either increase our confidence in a trigger or perhaps decrease our confidence as well, so we can further protect against errant retractions. There's some really interesting future work that we're going to do, but I'll skip that for the sake of time. I'd love to talk about it if you have any questions. But thank you very much for listening, and I'd love to have any questions.
Thank you very much, Zach. Right on time. So questions are welcome either by the chat, you're welcome to type them there, or if you have another question, I encourage you to raise your hand also. And I have several questions, so maybe I'll go ahead and jump in. Zach, this is a great talk. Thank you very much. So in terms of the long-term plan, so you said that this work might either increase or decrease our confidence in a trigger.
Right.
Do you intend to incorporate this information into the GstLAL trigger ranking?
Great question. So no, short answer. We've been very, very lucky and appreciative to have the GStLAL team contributing to this along with us, but we believe this to be beyond the scope of low latency operations. We think this is probably best suited for something analogous to a DQR task. I think that's probably where we will continue to work towards. Just because right now the analysis is somewhat computationally expensive. It relies on the classification of the gravity spy network, which also doesn't operate as fast as the search pipelines do. So right now we really are comfortable with it kind of being the overlap of the Venn diagram between DetChar and CBC searches. And we think that it's best served to continue to occupy that space, not in low latency, but with human advocate follow-up in the form of a DQ shift, DQ task. Okay,
very good. So I'll pause here. I could ask you many more questions. This is really interesting. I'll pause here and see if anyone else would like to jump in. Okay, maybe I'll fire you another one.
Please.
So let's see. So have you considered, so you've got these nice populations in terms of how the glitch classes are mapping into CBC parameter space. Sure. Have you thought about using something like a random forest to take those populations and then separate out between gravitational waves and glitches?
No, we haven't, but we should follow up offline because that's a fantastic idea. I think, we're not at all unlike, Leibniz and Newton inventing calculus at the same time, but in separate parts of the world. This is, to me, kind of the same train of thought. Let's compare real parameters and fake parameters, or, even better, parameters we thought were real and then turned out were fake upon follow-up with this analysis, so that maybe, we can add just one more, I keep coming back to one more check, one more box that will inform human reviewers of the likelihood that it was caused by a glitch or not. So that differentiation, I really think is the next step. Does this analysis effectively differentiate between real, fake, and ones that were thought to be real and turned out to be fake? And that's kind of what I was going to discuss in the future work. We would love to do a blind injection and recover a vanilla BBH, an NSBH, whatever the parameters may return in terms of binary system. We would love to see if the analysis can actually say, no, I believe those to be true, or if maybe they need to be watched a little more closely, supervised, if you will, to make sure that they don't misclassify a real event as being very likely to be caused by a glitch.
Okay, very good. Yeah, we should definitely follow up online. I'll note that there have been some studies that have thought about this from more of the parameter estimation angle. So Greg Ashton and Neve Shah,
Yeah.
thinking about glitch in signal populations and parameter estimation space. But yeah, they have a test set that I wonder if it might be possible for you all to look at as well. But I think this is really exciting to think about it from the perspective of the search pipeline.
Yeah. Thank you.
All right. Well, we still have another minute. And to avoid this being you and I talking shop the whole time, I would like to ask you a different question. So you mentioned that glitches are the bane of the existence of detector characterization experts. I agree with that. My personal bane is light scattering, and I was wondering if you might share with us yours. What is your glitch bane?
I also think it's scattered light as well, because that is one that is quite sneaky and quite frequent. I think something like a koi fish or an extremely loud glitch is really quite powerful, really quite strong, high SNR, high peak frequency. Like we can, there are gates and checks for those, but my goodness, scattered light, I feel is a chameleon, really able to appear in spaces where you wouldn't expect and keep reappearing in spaces where you thought you had previously banished it.
I wholeheartedly agree. An excellent summary of scattering.
Thank you.
Okay. Well, thank you so much, Zach. And thank you to Meg and to all of our audience members. This was a fantastic session. I really appreciate seeing all this great work happening. So we hope you enjoy the rest of the Amaldi meeting. Thank you, Margaret, for your help with hosting the session. And we'll see you all soon. Thanks everybody.
All right, looks like we are right at 9 a.m. So we should probably go ahead and get started. That's Pacific time. Hi, I'm Ansel. I'm a postdoc at LIGO Hanford. I'm just chairing this session. Looks like we're going to have 3 talks today. And we will start out with our first talk is Gravity Spy 1.0, Enabling Discoveries in Gravitational Wave Data Through Community Science by Christopher Berry. Before we get started, I want to just say a couple of words for those who haven't been to a session here before or just need a quick reminder. If you would like to ask questions, please write your questions in the Q&A box or raise your hand via the Zoom nonverbal reactions panel. If you'd like to ask a question you don't want to unmute, you can note that down in the Q&A box and I'll read your question aloud. And I think if folks want to unmute, I'll need to grant explicit permission to unmute on Zoom. There's something in the instructions about that. So if you're asking a question on audio, it might take just a moment to do that and I'll give you a verbal confirmation. With that, let's go ahead and get started so that we run on time, and I will hand things over to Christopher.
Hello, everyone. It's a pleasure to be here today to tell you a bit about the Gravity Spy project we have done so far. This talk will be followed by another from Jennifer, who will tell you about ongoing work with Gravity Spy. So I'm here on behalf of the Gravity Spy team, diverse group of different universities, and you can find more about our work in a variety of papers. I will highlight this last one, 2208-12-849, for our Gravity Spy data release, if you are interested in using any of our results in your own work. So here is a QR code in case you want to find a copy of the slides for yourself. I'm going to start off this talk introducing the idea of glitches, which are what we are interested in studying with Gravity Spy. And I'm going to go on to talk about the project itself. Gravity Spy brings together community science and machine learning to better understand the properties of glitches. And then I'm going to conclude telling you about some of the discoveries that our community science volunteers have made, which I think is a particularly exciting example of how we can involve the wider public with analysis of gravitational wave data. So first up, glitches. Those of you who were in the previous session on detector characterization will have heard about these already. Glitches are transient bursts of loud noise in our ground-based gravitational wave detectors. Most of the time, we're happy to approximate our noise as nicely Gaussian, but glitches do not obey this. And this causes problems for signal identification. They are a background source of noise. This is particularly problematic for low latency gravitational wave alerts, as glitches can be caused by instrumental or environmental factors. And if there's a change in the state of the detector, there can be a sudden rise in the rate of glitches, which can contaminate the background and put off the significance estimation and lead to false alarms being issued. Even if we do overcome the detection problem, we potentially have the issue of glitches overlapping our signal, which complicates the analysis of these signals. Over here, I have perhaps the most famous example of a glitch overlapping with a signal. This is GW17017, our first binary neutron star detection and our first multi-messenger observation. And here you can see the chirp of the binary signal going through the Livingston data, and this much louder thing on top is the glitch. This originally led to this signal being missed, and we had to quickly figure out how to subtract it in order to analyze the data, in order to tell telescopes where to point, in order to have a hope of finding out the follow-up. Now, there's a wide variety of different glitches, each potentially having a different cause. Here are some illustrations of different glitch types. This is showing spectrograms, so their time and frequency structure, to give you an idea of the different morphologies here. Now, different morphologies first tells you there are many different causes for glitches, and also that when it comes to data analysis, we need to be able to deal with many different shapes of glitches. So there's no one-size-fits-all analysis procedure to take care of glitches. What we really want in order to understand glitches is a large set of examples of the different glitch classes. Then for a detector characterization point of view, we have many examples, so we can go and correlate those with the state of the detector to see if we can identify a cause. And from a data analysis point of view, we have a large set of glitches, so we can test our algorithm to see how they perform against them. So this then raises the question of how do we assemble this large set of glitches from the different classes? And this is where GravitySpy comes in. So the goal of GravitySpy is to classify glitches. And part of this project is as a community science project. So we're hosted on Zooniverse. You may have heard of other Zooniverse projects, such as Galaxy Zoo. And we get members of the public, volunteers, to look at spectrogram images and classify glitches. Within GravitySpy, we then go beyond this and marry this to a machine learning approach to provide further glitch classifications. So we really have a virtuous circle symbiotically marrying together classifications made by volunteers and made by machine learning algorithms. So we start off with a set of glitch classes that were identified by experts. With this, we made an initial training set. We trained a machine learning algorithm with that. And then based on the output, we gave volunteers these glitches to look at. So we split our machine learning classifications into different levels. So we started volunteers off on the ones that the machine learning was confident of, in the hopes that those would be the easiest ones to volunteers to classify. And then as the volunteers got more experienced, we gave them ones that were more and more difficult to find. When we have many volunteers agreeing on a classification of a glitch, that can be then retired, and that can update the machine learning training set. We could build a larger training set. We can expand the machine learning algorithms capabilities. It could be more confident to distinguish different types of glitch because it has more examples. As the volunteers go through and look at many different glitch classes, they also find some things that don't fit nicely into the pre-existing glitch categories. This could be a new glitch appearing in the data, and we want to build up a nice set of examples of that too. So we can also provide our volunteers with machine learning tools to help search for more examples, and using this build up a set of examples of a new glitch class. We then get that back to our experts who can look at it, see if they can find a cause, see if they can find some correlation between the glitches to see if this really is a new class. And if it is, we update our machine learning model to include this new class. Eventually, we will hopefully converge in having a stable set of classes and some well-labeled data, which we can then give back to the experts who can go about doing their detector characterization or data analysis development using the labeled data set. Okay, so that's the big picture idea. In a bit more detail, this is how GravitySpy works. We have our training set of initial glitches. From this, we have a golden set of glitches. These are exemplars of particular glitch classes. And we feed our training set into our machine learning classifier. Those which are least uncertain, we give to our beginner volunteers. And we check how our volunteers classify glitches by looking at, do they get the right answer for the golden set or not? After they reach a certain level, after they've done a certain number of classifications, after they've successfully met a number of the golden set and got those correct, we level them up to show more difficult glitches and a greater variety of different glitch types. When we have a consensus of those glitches, those get retired and fed back into our training set. And things which are uncertain can be searched for with our similarity search tool, this machine learning tool, to hopefully find new glitch classes, which again, we can use to update our training set. As our volunteers go through the different levels, they start off very on quite a simple structure with just having two different glitch classes, these two different morphologies, and then the none of the above option for other examples. We find that this helps train the volunteers to understand what's going on. We clearly have different features in the spectrograms here so they can learn to distinguish that, and it also prevents them from becoming overwhelmed by the great variety of different glitches when they're just starting out. As they become more expert, they unlock more and more different glitch classes. They feel some reward in progressing, and they get more difficult options, and they are better at handling the complexity of the classification task here. For things which do fit in the none of the above option here, we can again turn to this similarity search tool, this machine learning tool I alluded to. And what's nice about the machine learning tool, aside from the fact that it can bulk classify glitches, is that it provides some kind of representation of the space that these images look in. So here we have a representation compressing down the high dimensionality of space that the machine learning algorithm uses to visualize the different classes of glitches and where they live in this feature space of images. Now, when we have something interesting, so something the volunteers want to search for more to see if there are things similar to this, we can use this representation and say, what are glitches around that one in feature space? Are any of those similar? This is an automated way to retrieve images that the volunteers can then vet themselves to see if they can find other examples of the new glitch they're looking at. So we have an online tool for this. Here's an example pane. We'll put in a glitch ID, say how many examples you want, and you'll come back with a big long list of glitches here. The volunteers can then go through and go, okay, this is what I'm looking for. No to this one, yes to that one. Build a collection, and from this build up a proposal to submit to our detector characterization experts to say, hey, I think I found a new glitch. Now, a particularly exciting example of this came in 03. Here we have two examples of light scattering glitches. These are glitches that arrive where we have light from the main beam, reflects off something it shouldn't do in the detector, gets scattered back into the main beam, and we get these little arches which are modulated by the motion of whatever the light is reflecting off. This type of glitch up here, referred to as slow scattering, has been around since the beginning of advanced LIGO. It was well known, but in 03 we had this new type of glitch called fast scattering, because it happens over shorter timescales, that was identified by our detector characterization experts and turned out to be extremely problematic during the run, I should say. Now, this new type of glitch was also identified by our volunteers. As they looked through images, they saw these, and they put together a proposal for a new glitch class based on their investigations. They named this crown, as they thought that these spectrograms sort of looked like the crown of a king or queen there. Because we had these two classes found independently, if you like, so we had experts retraining GravitiSpy who identified a new class they called fast scattering, and volunteers doing the same, we decided to do a comparison to verify how well the volunteers did at identifying a new class. Okay, so we trust from other citizen science projects that they're good at classification tasks, but going a level above, can they abstract the idea of a new class, is something that hadn't been tested before. So we retrained our machine learning model using the fast scattering class as proposed by our experts and the crown class as proposed by our volunteers, and compared the two versions of the algorithm to see how they did. So in this plot, I'm showing the results of running the classification on the other training set. So if we look over here on the right, this is what happens if you take our expert trained machine learning algorithm and apply it to the crown training set as put together by the volunteers. And you can see over 99% of the glitches identified by volunteers as crown were labeled as fast scattering. So the volunteers have done a good job at classifying things the same way an expert would do. Again, we know volunteers are good at classification from other citizen-science projects, so that makes sense. Over here, we now have the volunteer-trained machine learning algorithm classifying things that would be identified as fast scattering by our experts. And again, you can see the majority of glitches are identified the way you want them to be if crown and fast scattering are the same. When we looked at this, we were very happy. It was imperfect. Some things were slow scattering, which is a misclassification here. However, we thought the volunteers don't have access to all the auxiliary information that our experts have. They don't have any information about the state of the detector, for example. So it's maybe not surprising they didn't do perfectly. However, when we dug into this a bit more, we found that these glitches that were being misclassified all were very high signal to noise ratio, and they were misclassified because the examples found by the volunteers were all lower signal to noise ratio because they came from the engineering run before the start of 03, and the distribution of signal to noise ratio changed from the engineering run to the main part of 03, which we didn't know about before we'd done this investigation. What I will highlight is basically the volunteers didn't get this perfectly because they were too quick. They identified this new class before 03 started, and so this really highlights the power of having volunteers do things. They can really delve into the data immediately and give results. So if we'd been quicker ourselves responding to this, we might have been able to make more rapid progress in mitigating the effects of fast scatter. Okay, so let's take a bit more deep look into what we can do now that we have these new glitch classes and identify the causes of fast scatter or crown. It turned out to be linked to ground motion. We have materials vibrating, which the light is reflected over. What we have here is a plot showing the ground motion in the Livingston detector during a time when a train is passing by. And you can see we have peak of ground motion here as the train is closest. And down here, we can have the times of glitches that were classified as fast scattering or crown in our data set. So this not in the training set, but showing that we can identify glitches at an interesting time, which is what you'd want for a detector characterization study. Here you have the time, and here's the signal to noise ratio of the glitches. You can see that the crown is indeed missing out on the high signal to noise ratio ones. As I mentioned, that's because the volunteers didn't pick up on those because they were too quick. But potentially, if we had a symbiotic relationship, iterating a bit more with the volunteers on their proposal, we could have fed in a few more examples, boosted their training set, and hopefully we'd get better out there. Okay, so from comparing the crown and fast scattering, we can conclude that yes, volunteers can work similarly in terms of classifying glitches. They can identify new features in a similar way to our experts, and they can successfully abstract the idea that this is a new class of glitch. This is something interesting to look at to a comparable level of our experts, which is particularly exciting as this is a new way potentially to identify features rapidly in our detector data, feed that back to the sites to hopefully come up with new ways of mitigating the data or updating our data analysis. Okay, so I think I'm about out of time, so I'll leave up my summary slides and the link to the QR code for the slides if you'd like to download those and find more information.
Great, thank you very much. Any questions for our speaker? Great. Not seeing any open questions. I think we'll wrap up, and I know the round of applause is always a little underwhelming on Zoom, but I did see some people doing nonverbal responses for that. Thank you very much. And we will be able to hand things over a couple minutes early to our next speaker, who is Jennifer Sanchez, who will be telling us about GravitySpy 2.0, empowering the public to investigate the causes of glitches in LIGO data. So Jennifer, let me spotlight you really quick. If you could share your screen, then you can go ahead and get started.
Hi everyone, my name is Jennifer Sanchez and I am a graduate student at Northwestern's Research Center, Sierra, and I'll be giving this presentation on behalf of the GravitySpy team, and we'll be talking about GravitySpy 2.0, which is an extension of GravitySpy 1.0. So let's get started. Okay, so quick recap of GravitySpy 1.0. As Christopher mentioned, it is a 2016 project that is hosted on the Zooniverse platform. We have over 30,000 volunteers, and GravitySpy is really able to harness this power of citizen science to help the classifications of various different types of glitches, which are these noise artifacts that can complicate the analysis of a gravitational wave. So we have over 7 million classifications that have been made, but the objective of GravitySpy 1.0 is to be able to classify and categorize these different types of glitches that we have seen in the LIGO and Virgo detectors. So these classifications, once again, they help LIGO scientists better understand the nature of these glitches, as well as overall improve the overall accuracy of the detectors. So I kind of just wanted to emphasize that in these workflows, so in this plot that we have on the right, we have a spectrogram of a glitch class that the volunteers will have to label. And right now in GravitySpy 1.0, the main data that they're obtaining is data from the main gravitational wave channel. So now for GravitySpy 2.0, we're going to be giving them much more data. So for GravitySpy 2.0, we're building upon the success of the initial project by further engaging and supporting our volunteers' efforts in their glitch classification. So the project really hopes to explore the use of auxiliary channel data, which is data that is collected alongside of the main gravitational wave data. So these auxiliary channels measure various types of environmental or instrumental factors that can affect the data recorded by the detectors. So while the main gravitational wave channel records the primary signal of interest, so like a gravitational wave signal, it also picks up a variety of noise sources that can mimic or obscure a real gravitational wave signal. So these auxiliary channels provide information about the noise source, about the environmental conditions. So we really want to be able to kind of have a good understanding of the noises that we're seeing within these auxiliary channels to better understand and mitigate their effects on the main gravitational wave channel. And there's still much to understand about these glitches. So GravitySpy 2.0 holds this promise of advancing these research efforts to potentially explore clues, but at a much larger scale. So maybe providing some valuable insight and contributing to our understanding of these glitches. So the main objective for GravitySpy 2.0 is to be able to have our volunteers try to find these correlations between the main gravitational wave channel, which is what they're familiar with in the GravitySpy 1.0, and then now look at the auxiliary channels and try to see if there's some correlation between these channels. Okay, so this plot that we have here is an example of potentially applying another technique that LIGO scientists conduct when they are studying glitches themselves. So this plot is from a paper called Reducing Scattered Light in LIGO's third observing run by Sony et al. And in this paper, they address the issue of scattered light noise within the LIGO data. So the paper discusses various techniques that are implemented during the observing run in order to mitigate scattered light. And the plot is from a section where they talk about, they're looking at the signal to noise ratio of scattered light triggers and the ground motion in the earthquake and seismic band during specific time periods. So the x-axis that we're seeing is going to be the time, and then in the y-axis is the signal to noise ratio. And then GravitySpy, as Christopher had mentioned, so GravitySpy also employs machine learning techniques in order to analyze the spectrogram images. So to be able to classify them into different glitch classes, including slow scatter. So each spectrogram image corresponds to a specific time window and frequency range in the main gravitational wave channel. And the algorithm assigns a confidence score to each of these classifications, which indicates a level of certainty that the image belongs to a particular glitch class. So in the case of this top plot that we're looking at right here, we're only seeing slow scatter triggers with a confidence level that is above 0.95. And then this bottom plot is looking at the Omicron triggers in the XN transmitted light monitor during the same time. So this is like an auxiliary channel that we're also looking at. And then these vertical lines that we see here, these are just indicating the correlation between the scattering that has been observed in the main gravitational wave channel and then the noise detected in the transmitted light monitor channel. So this kind of shows how auxiliary channels can serve as a witness. So in this case, the transmitted light monitor serves as a witness for the slow scatter triggers in the main gravitational wave channel. So I think this kind of type of plot just is highlighting the importance of having our volunteers contribute in identifying / understanding these correlations between different channels. And it kind of demonstrates how our volunteers using GravitySpy can play a role in discovering and analyzing these correlations. So GravitySpy 2.0 is further empowering the volunteers by providing these enhanced tools. So we're going to be also giving them, like I mentioned, auxiliary channels to help them facilitate their exploration between these relationships between the main gravitational wave channel and the auxiliary channel. Okay, so now we'll go into a bit more detailed data flow for GravitySpy 2.0. So GravitySpy 2.0 will have 3 different phases, and we still have not deployed any of these phases, but we're super close on deploying phase 1. But we'll go over this workflow. So if we look at phase 1, our goal is to be able to have the volunteers decide if the glitch in the main gravitational wave channel has a similar shape as that of the auxiliary channel. So we're going to be having a few different levels for phase 1, and we have picked out what glitches we would like the volunteers to look at. So on the right, we have a few different glitch classes that we will be implementing for phase 1. So this includes extremely loud, whistle, and slow scatter. And we start off with LIGO. So we obtain data for from the LIGO detectors. We obtain the glitches in the gravitational wave channel and the auxiliary channel. And then for the glitch classification model, this is basically just the detector characterization experts that have helped us in like handpicking these auxiliary channels where they have seen strong witnesses for a certain glitch class. So we will be using these auxiliary channels in a workflow that we will be distributing to the volunteers. So these workflows are kind of just like a sequence of tasks that we're going to be asking our volunteers. And I have kind of like a mock, let me see. Okay, so we have like a mock of what we kind of want to distribute to our volunteers. This is an older workflow, but the idea still stands. So we'll have a glitch in the main gravitational wave channel, and then on the bottom, we'll have that auxiliary channel. And this is like the name of the auxiliary channel. And then we'll ask the question something along the lines, again, as if this glitch in the main gravitational wave channel has a similar shape as the one in the auxiliary channel. And then they can go ahead and respond yes, no, or I'm not sure. And we have some cool features as well. So if you go ahead and hit play, you can take a look at the glitch in different time segments. And then we can also hit this new like information button, which will give you a bit more information on the auxiliary channel. So this is looking at the different time segments for a particular workflow that you're looking at. So you can see it kind of zooms in, and you can have a better understanding of where that glitch is and specific frequencies. And then again, if you hit the information button, this new feature that we have now, it will be able to take you to this Wikipedia page where now we have the auxiliary channel that is now broken down into its name. So basically, this is it's a pretty cool feature because we can also kind of give them research papers so they can understand a bit more about these glitches. And I think this is really interesting too, just to have this additional knowledge that is going to be equipping our volunteers to contribute more effectively to the analysis and our understanding of these glitches. And it's kind of just allowing them to make these connections and observations beyond what just a visual inspection of these spectrograms would be. Okay, so now for phase 2. So again, we're still haven't launched phase 1, but phase 2 is still being developed, but we have an idea of what we would like phase 2 to look like. So for phase 2, now we will have the volunteers look at not just one auxiliary channel, it will be a few different auxiliary channels. And the idea is that the volunteers can then kind of cluster these auxiliary channels that they think are related to the main gravitational wave channel and put them in these collections. And then it gets fed to this machine processing where we obtain a similarity score, and this cycle kind of continues to be refined. But yeah, okay, so here is the idea of what we kind of want. So we have one main gravitational wave channel, and then on the bottom, we have these 3 different auxiliary channels, and we want the volunteers to see if there are relationships here. So just from us looking at this, we can see that maybe these 2 auxiliary channels may be related to this main gravitational wave channel, while this one seems to not really have anything there. So maybe it's not related, or perhaps maybe just during this event time, there's nothing there, but who's to say that during a different time, maybe this one will show something and one of these other ones will. But these are questions that we would like to continue to ask our volunteers so they can start thinking about these things. And then for phase 3, we basically now have the main ambition of our project is to be able to have the machine learning algorithm perform this automated causal inference. So the hope is to have the machine process analyze these relationships between the auxiliary channels and the main gravitational wave channels, and to be able to infer potential causal connections or correlations. And then the results that are obtained from the automated causal inference are then going to be fed back into the human causal inference, and then the volunteers can then analyze and validate the findings generated by the machine process. Okay. So just to wrap up, so on the volunteer side, Gravity Spy 2.0 is really empowering our volunteers by actively involving them in the research process and providing them with these necessary tools to think and conduct investigations as a LIGO scientist might as well. So we're hoping to foster engagement and collaborate between these citizen scientists and the researchers to overall help our gravitational wave science. And on the LIGO side, we are really hoping to utilize these auxiliary channels. So the project focuses on utilizing these auxiliary channels to identify correlations between 2 different channels, the main gravitational wave channel and the auxiliary channels. And these correlations can provide valuable insights into the origins and characteristics of just different types of glitches. So we're hoping that by engaging the volunteers, that this project can process a significantly larger volume of spectrogram images and compare these relationships, basically because LIGO scientists alone cannot do this. So it'd be really great to be able to apply this on a much larger scale as well. So with that, I'll take any questions.
Awesome. Thank you very much. Let's see. Any questions for our speaker? I actually have a quick question. How many different auxiliary channels are you looking at, and what kinds of channels are they typically?
Yeah, so I think we're still discussing exactly how many we would like, but for phase 1, at least right now, we would like to, as each level increases, to start producing a bunch more auxiliary channels. So that could be from like 10 to 20. I think we're still figuring out what would be a good number of auxiliary channels without overwhelming our volunteers. As for the type of auxiliary channels, I honestly can't speak too much about it because I'm not an expert in detector characterization, but from what I have asked when I'm trying to make these workflows and get a list of these auxiliary channels, it just seems to be different for different glitch classes. There are some auxiliary channels though that I've noticed that are shared, even though there's two different glitch classes. So that's also something that's pretty interesting to me.
Great, thank you. Let's see if there's any other questions for people raising their hand. We'll take a couple of minutes because we're actually managing to be a couple of minutes ahead of schedule, which is amazing. All right, looks like no further questions are coming up. So thank you again for a really excellent talk. I'm going to remove this spotlight. And it looks like we'll be able to start our third and final talk a couple of minutes early. So our third speaker is going to be Mikhail Korobko, who's going to tell us about GWECS, a new organization for early career scientists in gravitational wave research. So let me just spotlight you really quick. And you should be able to screen share, and then it is all yours.
Yeah, great, thanks. Thanks for the introduction. Let me just click play. Okay, great. That's right. So I will talk to you today about the new organization that we founded last year. It's called GWECS, Gravitational Wave Early Career Scientists. And here I'll talk on behalf of the GWECS Council, and you can see here the council itself. If you're not in the listening for the talk, you can just go to this website and read pretty much all the information is there. And you can also subscribe to our mailing lists and, well, find everything that might be interesting to you. Anyway, for the ones who do want to listen for the talk, let me talk a little bit about what GWECS is. As you, I'm sure, know, we have a lot of several different groups of early career scientists in different collaborations. It's VEX in Virgo, it's LEX in LISA, it's LAC in LIGO, and SPEX in PTA. And, well, what does it mean that these are groups of early career scientists? Let me quickly tell you who we understand when we say this is the early career scientist. Well, it's just anyone who identifies themselves as such. Of course, these are undergrads and the PhD students and the postdocs, but also junior staff members. It could be junior professors, could be some other types of permanent positions. Pretty much, if you think that you're still counting as the early career, then you are within GWECS. So these groups that we have in different collaborations, they, of course, unite the ECSs, but they also do different things. What do? They importantly bring up different concerns and needs of the ECSs to the organization, to the specific organizations that they have. They organize various tutorials, soft skill sessions. It could be online, it could be offline, for example, during the LVK meetings. They organize various workshops which are specific for the early career scientists. They could be, again, more focused on the soft skills or more focused on the science part. And importantly, they share different career opportunities. So jobs, grants, and stuff like that. What do we notice? We have 4 organizations, we have things that they do, and many of the tasks here are actually common. And so far, we did not have much collaboration between the different organizations. Maybe a little bit more between Virgo and LIGO, but still, we repeated the same tasks in different collaborations. So we thought, well, we should do something about that. And as gravitational wave field grows quite rapidly now, we see that there are a lot of gravitational wave science happening outside collaborations. And we would like to include those people as well into the science that we do, into the whatever opportunities we share, but also whatever skills we teach each other. So what do we do about that? Well, we create a new organization, which is kind of an umbrella and includes explicitly all gravitational wave ECSs. And it tries to it coordinates the actions across different communities that exist already, like Virgo, LIGO, LISA, PTAs, CAGRA, possibly in the near future, but also the future organizations such like Einstein Telescope, Cosmic Explorer, and whatever comes next. So let me read, before I proceed, let me read our mission statement. It's a little bit kind of high tone, but I think it's a nice one. So we think that GWEX is not really about creating just another gravitational wave community today, and it's not an attempt to create such gravitational wave community tomorrow. What we want to create a mechanism by which future generations of early career scientists can deal with the needs and challenges of their own times, by which they are confronted with the responsibility of designing the future of gravitational wave research over the effort of the past. GWEX is nothing but guaranteed dynamical, ever-changing continuity to a multi-generational endeavor called gravitational wave astronomy. So you see that in this mission statement, we are really looking ahead. We know that in 20 years, maybe, when future gravitational waves detectors are built, the people who are early career scientists now will be leading the effort then. And we would like to have the community that can talk to each other, would like to have the community that understands each other. And we know already now that it's not going to be possible to make gravitational wave science if we don't share tools, if we don't share language, if we don't share data. Gravitational wave astronomy is explicitly multi-messenger and multi-band, so to speak. So what do we do about that? Well, we unite and coordinate early career scientists all across the globe. Of course, we want to serve as a strong and constructive voice for the future of gravitational waves, as I just said. Right? We will be the ones leading the efforts in the future. Also address the current needs of the scientists and foster the healthy professional environment. We know that in the past years, there have been a lot of change in understanding what it means to have professional environment in science, and would really like to continue this trend and to support it. Share whatever career opportunities, grants, professional skills we can. And these three parts are already done by the existing collaborations. And what GWEX wants to add to this is building a new cross-collaboration channels through which we could communicate and ensure that we can have these common language that we will need in the future, that we use the tools that are shared across the collaborations, that we have the knowledge which is common for the benefit of the future of the gravitational wave community. Let me just make an example of what's happening at the moment. Well, imagine that we have two students who are working on the data analysis, for example, or stuff like that. And one student is in LIGO, the other one is in PTA. And they don't know about each other. Or maybe they know that the other one is doing something similar based on the papers. And they would like to reach out. What's the current channel? Well, they go to their PI. The PI would probably go to the group chair and try to find someone on the PTA side, to another group chair. This group chair will talk to the PI, and finally it reaches the student. You see, this is a long chain, and this is a long chain that also goes through the senior levels. It takes time, it takes a lot of effort, and it's very inefficient right now. So there is no way to build really connections between people through this long chain. And GWEX is designed to elevate that. We'd really like to create this horizontal structure between the early career scientists. So we have designed the organizations based on the also three-level structure. So as the actual body that designs and organizes and implements all the actions that we do, we have GWEX offices. They act more or less independently. So there are people who are within the offices and they decide what they want to do. They propose things, and there is a coordination office, and there is a secretary general and coordination generals, one of them at the moment. And we are basically just making sure that the offices can talk to each other efficiently. Not only to each other, all right, yeah, we have a number of people already on the offices, and among like at least 8 offices that we have at the moment. So well-being and mental health, which is very active, DI and social welfare, career opportunities, education and skill development, science and outreach, funding and sustainability, media and outreach, and just some tech support. So you see that there are quite a few people already involved, but of course we really would like to have more people involved in that because we have a lot of things planned and we need hands and minds to make this happen. So how does it work on the next level? We have the GWEX console, which consists of the existing chairs of the corresponding collaborations. So we have the chairs of Lisa, Virgo, LIGO, and PTAs. They are elected with their own democratic procedures within their own collaborations, but they all are on the GWEX console. And that means that we can talk to every collaboration through them, so we can reach every collaboration through them, but also we get like various things like overview on the people who are within each collaboration. We get statistics, we get some metrics, and we can use that to actually create efficient things that we want to share with the whole community, such as, I don't know, some kind of workshop, for example. So this structure allows to really coordinate all the efforts that we do within the organizations that are targeted to the ECSs and make sure that we don't duplicate the work, but actually amplify it. Yeah, these are just the faces of the current console, and that's exactly what I just said. So we have all the communities that exist already, but also any community that will come in place in the future, or all the people who might not have a specific representation are also here. And we will include them automatically. So GWEX is actually including everyone who's working in the gravitational-wave science at the moment. Just these people might not yet know about this, and we are hoping to reach them. So what's the current status? Well, as I said, we launched last year. We currently have over 200 subscribers on our own mailing list. We have the mailing list where we share job announcements, conferences, some media stuff, and some news, things like that. So these are the people who are actually, about half of them are not within any collaboration. So they're really outsiders with respect to the collaboration. Of course, overall, our reach is about 1,500 ECRs through the chairs of the corresponding communities. We have all the gravitational-wave collaborations except Kagra, actually, but hopefully soon we'll include Kagra as well. And we meet regularly, and we actually are very actively picking up momentum in doing useful and interesting stuff. Just to give you an example, what we've been doing till now, we had a Kickstart workshop back in 2021, which was explicitly for the early career scientists here in the Lawrence Center, and we focused it. It was an interesting format because we had it kind of half and half science and soft skills. That was very much appreciated by the attendees. but also by the community. So you see that here we published the meeting report in Nature Astronomy. So you can go here and read. This is basically the extended statement that I read in the beginning, but also describing what we had done there. Out of this workshop came out 2 more papers in Nature Astronomy as well, where we summarized the sessions and presented some overview on the future of gravitational wave detection. Last year, we had a series of talks on the well-being and mental health. I think we had 4 talks in total, and there are more in preparation. So hopefully soon we'll have more. And you see here are some examples. There is beating burnout and new work on healthy leadership, meditation and stress. And for these talks, we invited experts in the specific fields who really helped us to understand what and how to deal with these issues. Last autumn, we had a job fair, which was also quite well visited. So we had proposed jobs for undergrads, PhDs, and postdocs. These were academic jobs, but also some non-academic jobs as well. We presented in total 60 jobs, and we had people divided into parallel sessions where the different companies or people looking for the employees, they presented their jobs and answered some questions. I think that went very well. We had about 80 ECRs joining. I'm not sure how many actually found the job through this, but we hope that at least some. And we will definitely repeat it this year, the coming autumn. That's right. So in the near future, we would like to work actively with the offices. We have a lot of things planned. We are looking for new officers. So if you're listening now, you're interested in that, please do join. It's not necessarily a lot of work, but we need every person who can contribute a little bit in ideas, in time, on whatever. So you can go and subscribe to our mailing list, and then we'll share the information about this very soon. As I said, we have job fair planned. We have some mental health tutorials and sessions planned. And we hope to organize another one of these workshops next year, where we also will have kind of equal split between soft skills and science, like we did last time. That's that. Yeah, please join us. Well, actually, if you're the ECR, you are part of GWACS already. You just have to subscribe to the mailing list if you want to get some news and announcements. Go to the website, you can subscribe to our Twitter account. We actually try to amplify all the requests from the ECRs, ECSs. So if you have some exciting news, do let us know. We'll share this on our Twitter account. With that, thank you. And I would be happy to answer any questions.
Great, thanks very much. I see that we had several people kind of join during this last talk. So just for those who've recently joined, if you would like to ask questions, please feel free to either raise your hand in the Zoom nonverbal reactions or go ahead and type your question in the Q&A box. And I'll try and keep an eye on that in the chat. Any questions for our speaker? Well, once again, I actually have a question while we're waiting for others. So of course, gravitational wave astronomy has changed a lot in the last couple of years. And I'm wondering, do you see any challenges facing early career researchers that are specific to the current time that come up in your conversations in GWACS?
That's a good question. We see a lot of things changing, definitely, with the detections happening. And we see that a lot of load on the ECSs that maybe not always recognized properly, for example. So this is one of the challenges that we're definitely trying to think about everywhere in all collaborations. And yeah, I don't know. I'm not sure. On the top of my head, I don't think I have anything else to add to this.
Okay, thanks. I see a couple of questions in chat. We have a question from Swaraj. Would you like to unmute to ask your question?
Yeah, sure. Thank you. And so my question for you is, can undergraduate students join the WIC's offices? And if so, how and when can that be done?
Sure, we in principle welcome anyone who wants to be active. So please subscribe to our mailing list. So if you go to theguex.org, there is a subscription form. So the link to the subscription form right there. Once you're subscribed, you'll receive an email, and we will send some information about how to subscribe to the offices in maybe this week or next week. So we regularly post calls for new officers, and this will be the time for the new call. And then you just answer this, and then there will be a form, you subscribe, and you join the office, and then done. So yeah, you're very much welcome to do that.
Thank you so much.
Excellent. And I see another question from Christopher.
So if I read out, I was wondering if you had recommendations for how to construct a conference that really helps early career researchers, I guess, connect with each other and also promote themselves and get the most out of conferences.
Yeah, that's a good question. I don't have a good answer, unfortunately. So that's what we are trying to understand as well, because of course the conference for the ECR is something that is a little bit different, right? So on one hand, we have to manage the support, like the travel support, a little bit better. So like not everyone can travel to the other side of the world. So of course, like some kind of hybrid format is something that we are definitely thinking about. So what we did on the previous workshop, it was fully hybrid. And we had, so this Lawrence workshop that I mentioned, let me maybe go, oops, go back here, right? So this workshop, it was fully online. And what worked very well is that we organized a space in Teams where people could talk throughout the workshop about different things. So like discuss the talks themselves, but also just talk about different issues. So we had a number of channels where people could ask questions to each other, basically. And I think that worked very, very well. And we actually kept talking to each other after the workshop for a while, like for some weeks. So as organizing the online, I think this might be something to think about. For the offline conference, I don't have any good suggestion at the moment. We're still thinking about different options.
Thank you very much. Let's see, do we have some more questions? Thought I just heard somebody unmute. Maybe if you could raise your hand or type something in the chat. Okay, not seeing any further questions. So thank you very much. Both to our most recent speaker and to the two people who presented just before. This has been an excellent session and very nice to hear updates on both Gravity Spy and GWEX. And we are actually managing to finish 2 minutes early. So beautiful job staying on time, everybody. Thanks very much. Let's wrap up.